Today we are going to do section 6.4. First, let's look at the book. The last page of the previous page doesn't have much, okay? And I just zoom in here real quick. That's just one short introductory section. Next, page 192 and 193, which looks like, let's see, let me adjust this thing properly. Okay, that should be all right. And then, okay, and then the top. It's not zooming in very nicely, is it? Why is the corner so fussy looking? Then the bottom. Okay. I'm going to try again. Okay. Let's see. I'm not. Let's see. That seems a little bit better. And then the bottom. All right. Next, 194 and 195. All right. Here we go. That looks maybe trying to keep everything parallel. We should know how to do parallel stuff. Okay, and let's see, that is maybe like that. Okay, and then the bottom. That should be good enough. So let's get started on page 192. Please read the above introductory paragraph plus on the previous page by yourself. And now we'll look at section 4.1. We're going to define regions R theta and R the same way we define our X and our Y. Now however, we note that we're not going to include the pole, that is the origin, okay, the center of all the circles, in from our regions. For technical reasons, that doesn't matter that much in my mind. But anyway, let's move on. So our theta will be R of alpha, beta, phi theta, and psi theta. The right now, the alpha and beta are the angles. So theta is theta equals alpha to theta equals beta, and then the phi and psi are the functions that will vary. So the two angles are straight lines, whereas the phi and psi can change, wiggle and stuff. So then and the requirement is that besides the old requirements such as phi has to be continuous, psi has to be continuous, and phi has to be less than psi, that sort of thing. And then we also require phi to be bigger than 0 because it wouldn't make sense to go past it. And then and also that that is for the R of our theta. Let's visualize our theta, which you have done in the past. You've seen our theta before in basic calculus. That is, our theta looks something like this, okay? Which you have two rays, right? One is theta equals alpha, and the other one is theta equals beta. These straight lines, the two rays, and out of those, then you plot R equals phi of theta. That is, R is a function of theta, and it gives you some kind of a curvy line, curvy, wavy, whatever. And then R equals psi theta, same thing, that's on top. And together you will be able to bound some kind of area. Now, I want to emphasize that in this definition, in case you get confused, this our theta means the region of where theta is equal to alpha to theta equals to beta, and then the functions are phi, and psi. Okay, where the function phi theta, it means r equals to phi theta and r equals to psi theta. Now that seems pretty obvious, but it gets confusing later if you don't bear that in mind carefully. So so in my graph here, yeah, I have the r here are the equations I used to plot this specific graph. Not particularly important. I think they require, here are the requirements of our theta. That is, phi has to be less than psi, I think. It says that we need, the book says we need to obey the previous requirements, which means phi is less than psi. And then they also add that phi has to be bigger than 0. And yeah, phi has to be bigger than 0. And what was, and something about, let's see, what else does it say? Increment phi bigger than 0. That's it. Okay, phi bigger than 0. That's the only additional requirement besides what we used to do. And then so next, that's our theta, which we are familiar with, because I'm sure you've seen something like that when you first learned polar coordinates, especially integrating it. Now the next thing that you probably have never seen before, okay, which is our r. Our r is similar to our theta, except that now we're going to say that r equals to a and then r equals to b. Being that little r is the radius, then you know it's the two concentric circles. We'll start counting at a, okay, and then we expand it to b. So far, those are the constants. Except that now your constant line border is no longer straight; it's curved. Okay, so that makes it a little weird, but not as weird as the next sentence. The next part says phi will go, theta, that is the angle, theta will equal to phi of r, the first function, and then theta equals to psi of r. Now that, by now, is extremely difficult to visualize, because we don't do that much theta equals to function of r formulas in the past. So this looks completely unfamiliar. Now we assume that a is bigger than 0. And that is being that a is the extent of the radius. It doesn't make sense for it to be 0 or less than 0. So being that we're excluding the pole, as it calls it, or the origin, so then we assume a equals to bigger than 0. However, if your region does need to include the pole for some reason, we have to use some kind of limiting process, which yeah, we'll talk about that later. So let's look at the region R of R. What does that look like? I have plotted an example for you here. Okay, now take a look at this. I even shaded the region to make sure you know what it is, because it looks so weird. All right, now first, let's start with R equals to A. That's the smaller circle, right? Extends. So R of R goes from it calls R A, B, phi of r, psi of r. That looks familiar enough. So we start with r equals to a, the smaller circle. That's fine, which is required to be bigger than 0. That makes sense. And then goes to r equal to b, the bigger circle. That's still okay, right? And then look carefully. Okay, now from this point on, things look weird. Phi equals to, theta equals to phi of r. Where is that? If you look for right here, the red line, see the red line goes this way? That's theta equals to phi of r. Okay, specifically in my case, theta is just equal to 2r, is where I plotted this. I plotted this with the polar coordinates, and all you type in, you can't type in this thing, okay? Because Desmos doesn't do theta equals whatever. It does do r equal to something too, though. So to plot this line, what I did is I plotted r equals to theta over 2. Is how I plotted this red line here. So anyway, for us, however, that's the theta equals to phi of r equation. Next, theta equal to psi of r. Where did that go? That is over here, the black line, okay? That winds clear around there. So you see the shaded area, which is r of r. And remember, for r, this thing is very different. R equals to a, r equals to b as the first two numbers, and then theta equals phi of r and theta equals to psi of r are the two end functions, and it ends up looking like something like this, okay? In other words, there is no straight line anywhere, right? I mean, even our theta has at least 2 straight lines on borders. Now all sides are curved. Or wiggle. I mean, well, 2 of them are just part of circles, so they're not curved too badly, but still they're curved, okay? And when they're curved, they can look really, really odd because the curve can go clear around, and so really bend your mind, so to speak. But so spend a little more time staring at this until your brain get used to it, as to what is the region R of R, okay? And the black line I drew it as theta equals to 3R. Or on the Desmos calculator, I actually typed in R equals to theta over 3, because it's not able to plot theta equal to any function of R. It says we're not ready for it yet. So maybe by the time you use it, it'll be ready, hopefully. But anyway, so that is how I plotted this. And look at this very, very carefully, okay? So spend a little more time looking at this thing, and maybe make up something yourself, okay? Make up our region yourself, just to familiarize with this thing, because this thing is super different from this. You've seen this, you know, a couple thousand times from elementary calculus. This is not near as big a deal as this thing. This thing is so weird, and plus you've never seen it before, so your brain is not quite used to it. But staring at it long enough, your brain can get used to anything. That is that. And next, we are going to look at, let's continue. All right, so let's consider the region R theta. R theta is easier, more familiar to us. All right, our theta equals to alpha, beta, A, and B. That is just a slice of a pie with one corner cut off, okay? And so, because everything's constant, so that's pretty easy to visualize. The region between, theta equals alpha, theta equals to beta, and then circle R equal to A, and then R equal to B. So a slice of pie with the tip sliced off for your little brother to eat. Yeah, I used to do that all the time with the pizza, because I don't like the top part. I only like the crusty part. So anyway, R equals to A and R equals to, all right. So then, well, alpha and beta has to be limited between 0 and 2 pi, otherwise it doesn't make any sense. And then A is, of course, bigger than 0, and B is bigger than A to make sense, okay? And so it says, the next thing it says is, by elementary integration, the area of this thing that we just described is equal to 1/2, etc. You might not remember that formula. Like, did we really do that? That might not look that familiar. It's maybe somewhat familiar. Here's the formula. So I copy and pasted the formula. This is from calculus 2 or 3. Okay, they both cover it. Calculus 3 is in the beginning. Calculus 2 is at the end of the book. Either way, it's the same thing. The point is, the area of such a region bounded by a polar curve, this is calculating from the origin, that is from 0, okay? The full slice of pie, the equation is this. So then if you have this cut off a smaller slice, then there's a subtraction happening. But the point is, here's the formula, okay? The formula is 1/2 R squared, and then the derivative of d theta, where R is equal to f of theta. So that's where the book got this. If you don't remember that formula, let's just say it. You did learn it, and let's not think too hard about it, okay? And so there's where the formula comes from. The area is 1/2 of R, the first R squared minus the second R squared. And then, and if you replace the first R by R equals to psi of theta in general, then the formula will turn into this. So either one is the formula, okay? And so that is that. So next, let's look at theorem 3, the fundamental theorem. So let's look at theorem 3. We have f theta and r that is continuous, of course, in the closed region. And then r theta is defined as we mentioned earlier. Now this theorem only is good for r theta. I mean, it's only proving for r theta. It also applies to r, which is described in problem 10, but we're not going to do problem 10 in the homework because it's just more or less a repeat of this thing, and I really don't want to do it again. So, but we'll understand that once we prove this, that we can use this for R as well. And so anyway, keep going. So so what about it? What that means is now the same thing. The double integral is equal to the iterated integral. In other words, we know how to calculate the double integral that's beyond using limits, okay? And there's a nicer formula for it. So that's what we're trying to prove. Now that this formula, this thing looks similar to the rectangular version, right? And we're also going to prove it in an almost identical way. And the first step, we'll suppose the bottom function phi is equal to some constant. In fact, we're going to assume that it's 0, okay? We'll assume it's equal to constant a, which is set as 0. And then we'll proceed as we did before. So I have a scan here. And let's see, I have it such that I have both of them lined up so that you can compare them in. So this is the one we're doing right now, and on the other side, that's the old one for reference. So we are right here, okay? Now, first we're going to set delta theta equals the beta minus alpha divided by some n. Just like on the other side, delta x is b minus a over n. As a result, theta k is alpha plus k delta theta, okay? Just like the other side. Next, we're going to define f of theta, big F, which is, from this point on, we'll pronounce that symbol up there as phi. For obvious reasons. So f theta is integral from 0 to phi of theta, small f of theta r dr. There's another r in there, okay? And there always is in polar coordinates in integration, which is similar to the old one of f of x, right? And then, so then the next thing we're going to define is the integral from alpha beta which is by its own definition is the limit and goes to infinity, where you have a bunch of small ones, okay, equal to f psi. This is done by the mean value theorem. That is, we break it into the small chunks and yank big F out of each small integration, okay, and add it up, because then the small integration end up being just delta theta, and then add it all up and becomes the big integral, and which is similar to what we did in the past. See, it looks almost identical. So next, let me move the screen up a little bit. All right, next we're gonna choose psi of k such that, and let's see. Oh, I forgot to mention the psi of k, right. I think this sentence is, I believe is referring to this statement. Psi of k is chosen by MVT. No, I think this statement, psi of k is random. So we don't have to choose it specifically, just anything that's, actually, let me think about this. All right, that is, I said that wrong. This psi of k is just any old psi of k that's within the range, within delta x or delta theta. That is, the psi of k is, because this is a limiting process. So this psi of k is random, okay? Anything in there would do, because n is going to infinity, so it's all forced in no matter which one you pick. So this psi of k is not restricted except as long as it's within range. Whereas this one, we're going to specifically choose psi of k, just like the previous problem, such that this equation stands, that we can yank it out. That is, it becomes the area of that little slice, just like the other one right here. See, we plugged the psi of k out specifically by MVT, and then we're going to do the same thing here, except that here we're going to use the area formula. That one, the area is this thing, okay? And this one, we have to use the area formula, as we have seen, is some kind of squared and divide by 2, as we mentioned a little while ago. So that is the area formula. So then next, what we're going to do is we're going to let mk is the minimum of phi of theta from k minus 1 to k of theta, just like before, same deal. Right, and then we're going to draw a bunch of subregions. For the bunch of subregions are defined by the circles. This is a circle. R equals I triangle RK, where I goes from 1 to n. I have some drawn here. Okay, these things are all the R's. Just like before, we used to have this is the old case when we draw y equals I delta y of k, with everything else look identical or almost identical. and these are the horizontal lines that we were drawing, and we were adding these things up, and now we're going to add these things up. But they besides looking slightly bent, they are identical in formula form, or almost identical. See? So we'll continue doing that. And so with all that, then f of psi of k, what was f theta? It's defined way up here, right, in both cases, is equal to the sum of, let's see, so then f of psi of k equals the sum, and then we're integrating this thing along r, because along the line, okay? So we're going from I-1 to n, and then to this part all the way to psi of k. And just like before, see, this is what we did before, and we're following the exact same pattern. And before we were integrating along a straight line. This we're integrating. I'm not sure, but psi of k is. Well, I think we're integrating also around a straight line this way. But whatever. The point, we don't even care at this point. The point is we're doing the exact same thing as we did before. So the next step, we are at this point, right? Now previously, in previous case, we yanked the f psi y out, becomes, found some eta ki, such that f eta ki get yanked out of the integration, so that the integration disappears and so each integral over here, it becomes delta yk. At the bottom, it just becomes that thing. But anyway, it got yanked out by the MVT. Over here, however, it's not so simple, because we have the function f, right, is in there just like the other one, but we have an extra r there because of the polar integration. The polar something, whatever that we're doing right now, there's an extra r in there. So we still have to yank out f though, and so what we'll do is going to use the MVT, which has a corollary 3 that will deal with this. Now let's look at corollary 3. This is on page 162. All right, and now look at corollary 3. What does it say? If you have a function g that's bigger than 0, then if you have f times g, okay, then you can yank out the f with the g still in there, with f value equal to psi or something like that. See? So that's the one we're going to use. We'll yank out just the function f and leave g will be r. Okay, in this case, we'll leave the g in there and yank out the f. So there exists a similar eta ki. We can yank it out, and that's the first part, and that's the second part. The integration limits are slightly different, come from here, but the story is the same. That we can leave the r in there, as corollary 3 says, and only pull out f. All right, so the next step we are going to do is slap a triangle on it, okay? And in the summation sign. So we got here, and we'll do the same thing was done on the other side. By the way, this one, I think the summation sign applies to the bottom part as well, I believe, or something like that. I'm not sure. We'll worry about that later, okay? So the point is, whatever we did before, we're going to do a similar thing. Yeah, this summation sign also applied to the next line. I just didn't have enough space. So anyway, so if you slap the triangle on there and the summation sign on this thing, then what we have is a bunch of f of psi k eta ki, and then times the triangle theta. And triangle theta times that is each individual area. Now this is a bit of a bunch of details that you just have to stare at it until it all makes sense to you. Specifically, notice this part, okay? That being that this is the area, area equals to this, and also the k plus 1 goes up to psi of k, the integration does, and we had this formula from earlier as why this is also the area, because of this formula. So please look at that enough and it will all make sense to you. That work out all the details, okay, why that is the area and stuff, and all the formulas come out. So please confirm all that. And then, so following the previous pattern, okay, so the next step we got in previously is this equation right here. which is delta sk is the area of each little subdivision. We have identical thing here, and as n goes to infinity, then this thing will be equal to that, which is the double integral, okay? But this is the iterated integral. So just like in the previous case, the iterated integral is equal to the double integral, and that finishes the proof. So please pause this video now and look through all the details of the formula, especially this part yourself. It takes longer to explain this than for you to just stare at it and then finally realize what's going on, especially this part. Okay, and after that, then let's move on. Next, let's look at page 193, where we'll have example A, find the area of a circle. We're right back to 5th grade, yay! So we calculate the area of a circle, as it says here, and notice that instead of going from 0, they are very careful in using epsilon that's bigger than 0 to do it, and then letting epsilon go to 0, which doesn't really change anything. So as the book says, so please do that integration yourself. It's very straightforward, I think. But normally we just ignore the epsilon and come up with the answer anyway. However, it does mention that theorem 3 is not proven for regions that includes the pole. So you do have to be a little bit careful here, but I think most of the time you just, it just kind of does. But bear that in mind. So if a situation doesn't work, then you know why. Oh yeah, there was that pole problem. All right, so please do example A yourself, and let's move on to example B. Now, example B, we have a semicircle, y equal to a squared minus x minus b squared, which I have drawn right here, okay? That if you square both sides, it becomes y equal to y minus 0, okay? So the center of the circle is at 0, comma b, right, which I have drawn right here, and it has a radius of a. So I have drawn right here. So we only care about half of it. So the semicircle is all we care about. And what the semicircle is going to do is going to be rotated in the xy plane above the origin through 90 degrees. What that means is we're going to do this. Okay, I'll draw it right here, and you can draw it yourself as well. There's a circle, and something like that, and it end up looking like this. All right. So then this area inside here, the new path, which doesn't include the inside of here, okay? It only includes, but it does include the inside of here. So is this area right here going all the way across, and this kind of thing, okay? And this part also. So that whole thing, what do we want with it? Let me see. The region which find the area traced out. Okay, find the area for the for that thing that I just came up with. And anyway, so if you draw this on Desmos, it'll look much better. But anyway, yeah, I don't know that it's worth us drawing it on Desmos. First, we need to figure out what is the equation of the semicircle in polar coordinates. And what is the equation? The equation is called theta equal to f of r equal to all that other stuff, okay? And that stuff is that looks complicated until you think about it a little carefully, and then realize that it is indeed that. That is the point, and that follows the law of sine equation right here, where we have here's the explanation. What is that? I can't even read this stuff. And this is that's, well, whatever that is, I don't know. But anyway, this is a explanation. That is r squared plus b squared. B is the distance here. In the little triangle here, r squared plus b squared minus 2br cosine theta is going to be equal to a squared. That is the law of cosine. And then you yank cosine theta out of there. I mean, yank theta out of this equation. Then you get this, which is a function of r, right? So then theta equal to function of r will be the description of that thing. Yeah. And anyway, so that will be f of r, is that complicated equation, okay? But that's already given to you, and it's given to you for a reason. It's because we won't really need it, and then so that's why they gave it to us so freely. We won't use it anyway. So the area, according to the formula, iterated formula, is going to be find the endpoints very carefully. The radius goes from b minus a, okay? So the radius of this region goes from b minus a, this part, all the way to b plus a, this part. So that's the R variation, okay? So far so good. That's R. And then how does theta vary? Theta will vary from this curve, where theta is equal to f of r. That's this curve down here, as we mentioned here. And then up here is the same curve except theta plus pi over 2. So that thing is this thing plus pi over 2, okay? Because we're measuring the angle here. R of r is a bit hard to bend your mind around it, but just force yourself to keep staring at it until it does make sense to you. So anyway, so that is the top. This is phi of r basically, and that's psi of r in the definition of R of r, which I'm going to show you again. Which is right here, okay? Remember the definition of R because it's weird. So please write this down and stare at it as soon as you need as you need to. Maybe take a screenshot of this screen or something. But anyway, R is defined as R equals A, then R equals B, then phi of R is some function of R, but it defines is a theta equals to phi of R, and then theta is equal to psi of R. That's how the functions, those two last functions are defined. Okay, now bear that in mind. We'll make this thing look a lot clearer. So then we have our R of R properly defined. Once that is done, then we can integrate, right? That is theta. R goes from b minus a to b plus a. Theta goes from fr to fr plus pi over 2. And when you do the integration, you notice that the f of r, as complicated as it is, just subtract itself out, so it disappeared. And then we only have something somewhat easier left. Okay, we need to evaluate this thing, which end up being a times b times pi. Yeah, is that right? I think so. Let me check here. That is pi AB is the answer to example B. All right, so the only hard part really is just to manipulating region R, that you have to be very clear in your mind. Don't confuse it with region R theta, because it's very easy to do, because R theta is what we're used to. R, we're not used to it. So yeah. Anyway, let's then now look at the next page and look at example C. We are finding the mass of something that is proportional to the square of the distance from the square of the distance from a fixed diameter. That is right. So let's say we have this is a circular object, okay, and so the diameter is this thing right here, the vertical diameter. So as a result, we will say the density is x squared. See, here's x squared. So the density is proportional to x squared. All right, so knowing that, well, that doesn't really change much of anything for us. So then we are just going to do that. Now, R, as we remember from basic calculus, x is R cosine theta. Okay, we just plug it in there. And then calculating this thing, remember the x goes sideways, right? I draw a couple of them there to remind you what it is. And although I don't think it matters, you just plug it in. And our theta, we're doing our theta, so angles, it says theta you have to calculate from epsilon or something. I'm not sure why. Well, whatever. The point is, we'll do this and let epsilon go to 0 anyway, so everything works out nicely. Okay, and the integral of this thing is yeah, it's probably not that hard to do, but I didn't want to bother doing it, so I used the calculator. Okay, this is the Wolfram calculator, which can do double integrals with letters instead of numbers in the limits. Okay, so, and plus they can do dr, d theta. So they're very, very smart. And anyway, after I cranked this out, I typed it in and out came this thing. And so I just want to show you how to use the calculator. And in case you want to do so and know that it is very, very intelligent, right? It beats the heck out of TI-84. Ugh. And so anyway, that is the answer. So with that, we have come to the end of this section, and let's talk about homework. So for homework on page 194, please do problems 1, 2, 5, 6, 7, 8, 9, 11, 12, and 13. And when you're done, I want to talk about them. All right, so now let's look at problem 1. Problem 1, not much worth mentioning, I don't think. You just plug it in, and I just typed it into the, well, I don't know what I typed it in. I might not have typed it in anything. It's a short answer, you know, a one line, and I got the answer, so that's it. Problem 2, similar, except that you have to work out a fairly complicated formula, where by applying law of sines, and work with your triangles, right? And then eventually you get r equals to f theta, and f theta equals to that thing. And then we're gonna apply it in the integration. Yeah, so once you do that, then the integration come out, and I plugged it into the calculator. It says that the answer is this. This answer isn't identical to the answer in the back of the book. The answer in the back of the book says something simpler, okay? It says this part. But if you work with it, then you very soon realize that these two things are the same. So that's problem 2. Next, problem 3 or something, no, 5. All right, next one, we're going to do problem 5. We're going to integrate the infinity sign, which is fine. They're called what, lemniscate or something? The problem is that there is a square root situation here, and so you have to integrate very carefully. You can only do this stuff from minus pi over 4 to pi over 4. The rest of the time, cosine 2 theta is not defined. And if you integrate over it, you're going to add the garbage, and which will ruin your answer. And you will get, I think in my case, it just collapsed into 0, and I couldn't figure out why. So after much trouble, I eventually realized there's a square root, a catch of the square root, okay? So you have to be very careful with that, and once you do that, then the integration comes out nicely. Where's the answer? Did I even write down the answer? I don't see the answer anywhere. Why is that? Let me write down the answer. All right, so I got it down. There's the answer, a squared over 2, and that should be okay. And problem 6, that's really straightforward. I don't think anything interesting happens here. So you just crank it in, and I typed in the calculator, and then there's the answer. Problem 7 is, yeah, not much happening there, I don't think. We just do that. And problem 8 is similarly, we just don't forget to use the MVT corollary 3 on page 162, where it allows to yank out the function from the from inside the integral, and then the a would be equal to what they want, okay? All the stuff. And yeah, so that's problem 8. Oh, I forgot to show you this what I did for problem 2, the integration. It's not that hard of an integration, yet I was impressed that the Wolfram calculator can do this, right? And is able to crank it out, so I don't have to wear myself out thinking about this kind of thing. So yeah, and that is not a big deal. So next, let's consider problem 9. Problem 9 is the summation of something, yeah. Anyway, I don't think there is much going on with problem 9. We add it up. We just have to, yeah, we have to yank it out and then do the subtraction. The reason we can yank it out is because the MVT corollary 3, okay, that we've been using for a while. Otherwise, there's not much to it. And problem, what is this? Problem 11. This is problem 11. Problem 11, we have to calculate this thing first by our theta, which is simple enough, more or less, and then by our r, which is harder to think of, okay? And it's because of unfamiliarity with our r. But after some struggles, I was able to get it to come out. And I think I have a graph for it too. Actually, I don't have a graph for problem 11. I think the most important part actually is just remember this, okay? That what is our R and what is our theta? Our theta is this stuff. Please take a screenshot of this if necessary to remind yourself what are we talking about. Especially if you do both problems, you get yourself confused very quickly. I mean, I do. Just you know, which is theta and which is R, and it's all getting lost. So remember, theta equals alpha, theta equals beta. And in here, R is equal to phi theta and R equals psi theta. And for R of R, the story is completely different. Now R is A and R is B, and theta is equal to phi of R and theta equals psi of R. Okay, once you keep that straight, then I think the problem is quite straightforward. Next, let's look at problem 12. Now the problem 12, we need to find the area between something curve theta equal to sine R. And the line segment theta equal to 0, and then R has to be between 0 and pi. Okay, now this problem, has nothing really hard about it, except that when we need to see what this thing look like, pretty much. And to see what it looks like, then to plot it is hard, because Desmos doesn't do theta equals to function of R's. It only does R as function of theta, which is in this case, then I have to change the domain to figure out where does this thing end. See, and but eventually I figured out this is the second part of that same function. So the green and the red together makes R theta equal to sine of R, and the bottom line is theta equal to 0. Okay, and the radius goes from 0 pi. And then the function is 0 and sine of R. Now I have the R of R definition here again for your reference in case that your brain feels confused. And anyway, so once we figure that out, then the integration is very straightforward. We will let's see. Here's my notebook. So we'll go ahead and integrate, and that would. So after we integrate according to the formula for integrating R of R, then we get pi. Okay, and when I was looking at that graph I plotted, I estimated the area is roughly 3.2. So the area ended up being pi. So my estimate is pretty close to my estimate. And by estimate, I mean I stared at this thing right here and tried to count the squares on the inside, you know, and make a guess of how big roughly this area is. And so the answer is pi, so that should be correct, being that it's very close to what my estimate is. So next, let's look at problem 13. Problem 13 is, first let me read this thing. Problem 13 says we need to find the integral of the function 1 minus R squared square root over the region, some region. All right. And so let's integrate this. Now again, there's a square root. See, the square root, you have to do it very carefully, because within the square root function is an implicit absolute value. I mean implied absolute value function, right? So if you're not careful, then you might cancel out your result and end up with 0 for no reason. Which is why the book says, watch out, because this answer should be positive. All right, so that is So doing that, what I did is just split the function into two parts, the positive part and the negative part, knowing that they should come out the same. That way I don't have to worry about the stupid thing turning negative on me. And so that's what I did. And see, here's problem 13. Okay, I plugged it in like it says, but I only went from 0 to pi over 2. And then I came out with some answer. I messed up a little bit, but eventually figured out the right answer that checks out with the back of the book. And notice that because we're integrating sine to the power 3, sine to the power 3, which comes from sine squared, take the square root and then raise to the power 3. So it's actually, we're doing the absolute value of sine theta to the power 3. And that's why if you do the negative part, and they say if you integrate from minus pi over 2 to pi over 2, that thing will give you a 0. Then your volume is 0 for no reason. And but once you watch out, then the integration comes out quickly, especially if you type it into the calculator. Now I have graphed the thing itself as well just to look at it. Let's see, and in the meantime I can't find problem 13. Got it. All right, so it is right here. Here is problem 13. You have watch out your limits very carefully. Okay, here's the function. We only care about half of it, the half that you can see here, and I draw it closer. And the half you can see, we only care about the air, this part, the air part. Okay, and the green, what's inside the green thing, we don't care. We're only calculating this area from here to here. So that is that's what we're doing here. I'm not sure this graph is particularly helpful necessarily, but it's good to look at it. And then I like the 3D calculator and like to graph if I have whenever there's something worth graphing. Yeah, so that should be. My screen doesn't seem very bright. Doesn't matter. I guess you can see it clearly enough. And here are the formulas I used to do the graphing. That should be it. That should be the end of this section.